Hello. In this lecture, we're going to be introducing the first law of thermodynamics, which is really a restatement of the conservation of energy law, which basically says that energy can neither be created or destroyed, it can only change form. And so if you think about the energy that the Earth receives from the sun, that energy can be transformed in many different ways. It can be transformed to radiant energy, it can be transformed to sensible heat, it can be transformed into latent heat, and that energy can be moved around the Earth system. And so the first law of thermodynamics is our bookkeeping methodology for being able to keep track of the energy that an air parcel or the Earth's atmosphere receives. The most fundamental form of the first law of thermodynamics is dq is equal to du plus dw. This is the intensive form where the dq is the amount of heat per unit mass that's actually put into a system. So how do you put energy into a system? Well, you can have the input of radiative heating or the export of energy through radiative cooling. Or you can have the latent heat energy storage or latent heat energy release. And by definition, dq is greater than 0 for input to the system, and dq is less than 0 for energy that the system is releasing to the environment. So dq is the amount of heat input into the system. du is an increment to the internal energy of the molecules of a system. And that increment to the internal energy can either be through the kinetic energy of the molecules of a substance or the chemical potential energy of the molecules of a substance. And the last term in this form is that you have dW, which is the increment of work that the system is doing to its environment. If work is being done by the system, then dW is defined as being greater than 0. If work is being done on the system, then dW by definition is going to be less than 0. And for a gaseous situation that we have in the atmosphere, the work done on the system is due to expansion or compression. So in essence, if you put heat into a system, dQ, it can do one of two things. It can increase the internal energy of the system by increasing the kinetic energy of the molecules of a substance or the chemical potential, or it can do work to expand the surroundings. So what we've been looking at so far is the intensive form of the equation. Remember, the intensive means that it doesn't depend on the amount of mass that is in your system. The extensive form is the form of the equation that does depend upon the amount of mass in the system. And to differentiate the extensive form from the intensive form, we actually use capital letters instead of lowercase letters. So d capital Q is equal to d capital U plus d capital W would be the extensive form. To get from the extensive form to the intensive form, you would have to divide both sides of this equation by the mass of your system. So let's look at the individual terms associated with the first law of thermodynamics. Let's start with the work term. So the work done by a system, if you think back to physics, is defined as dW is equal to pressure times the increment in volume. And so if we have a PV diagram, which you might remember from physics, we're at increasing pressure here, increasing volume here, and if we happen to have a volumetric expansion or a volumetric compression. In this case, we're doing a expansion, so we're going from V1 to V2, where we're expanding this, but we're also simultaneously decreasing the pressure, which would result in that expansion. If you do an integral underneath this curve on the PV diagram, you actually get the work associated with that. So the work is the integral of P dV from V1 to V2. If you want to move from the extensive form of the equation, which you've seen in physics, to the intensive form, which you'll see in this class, you need to divide both sides by mass. So d capital W divided by m is defined as d lowercase w. And then the change in the volume divided by the mass is actually the change in the inverse density. And if you recall, the inverse density is defined as alpha. So in the intensive form of the equation, we have the change in work is equal to defined as the pressure times the change in the specific volume of the gaseous system. For the internal energy term, that would be the dU term, we can define dQ as the temperature. If you raise the temperature of a unit mass, it requires a certain amount of heat increment. And the amount of heat required to raise the temperature of the molecules of a substance can be defined as the specific heat. And we're going to define this as a specific heat at constant volume. So in this case, the amount of energy required to raise the temperature of the molecules of a substance requires a certain amount of heat input. And the specific heat is the ratio of the amount of energy that you put in for the amount of heating that you get for a given substance, and this is done at constant volume. If you want to turn this from the extensive form to the intensive form, you need to divide both sides by the mass of your system. In this case, we go from a capitalized CV, which is the specific heat at constant volume, to a lowercase CV to signify the intensive form, and we went from capital Q to lowercase q. So by definition, the specific heat is equal to dQ over dt, in this case, not as volume is constant, but as the specific volume is constant, which is 1 over the density. If you move back to the original equation of the first law of thermodynamics, dQ is equal to du plus dW, at constant volume or constant specific volume, the work term actually goes to 0, because the d alpha is equal to 0 or the dV is equal to 0. So that term goes to 0. And then you can use your definition of specific heat and solve for dQ to put into this equation. dQ is equal to du, solve for du, and you'll end up with the internal energy of the molecules of a substance is equal to the specific heat at constant volume times the increment in temperature. Likewise, for the extensive form of the equation, you get d capital U is equal to capital CV times dt. And if you put it all together into the original forms of the first law of thermodynamics, you get that dQ is equal to C sub V dt plus P d alpha for the intensive form of the equation. And for the extensive form, we get d capital Q is equal to CV dt plus dV. These two are two forms of the first law of thermodynamics. We will be deriving further forms of the first law of thermodynamics that will be more useful, because it's very difficult to measure the change of volume of an air parcel or the change in the specific volume or the inverse density in practical matters. And so we're going to redefine terms and come up with additional forms of the first law of thermodynamics that may be useful to you when you're conducting certain types of calculations.